back up in the game. Science. It's that time of week. It's your favourite show, actually, I believe. Cornwall's Science Sessions here on the Source FM. Got some great stuff planned for you today. With, of course, myself, Ben, and with my extremely handsome colleague, and that will be Sam. He's just sitting right here.
How's it going, Ben? How have you been this week?
Fine, thank you. Well, I think you'll probably feel a bit better this week, won't you, mate? Because you're not blindfolded and I haven't got chili peppers for you to try.
I feel a lot less stressed this week. Last week was terrifying, and it ended up fulfilling all the fear that I had within me. So this week, it's a lot more relaxing. Well,
yeah, I did like that. Tune into that one again. We've got it on SoundCloud if you want to hear his pain again. Everyone likes Sam to be in pain.
Yeah, apparently.
Yeah. I went to the Isles of Scilly recently, mate.
How was that?
Really amazing. Really, mate. They're doing a locals offer actually at the moment, which I wanted to mention. I think it's £25 if you take a proof of your Cornish address, your residency. So, well worth it. Amazing place. Had a cheeky lager in the sun. The sand was the thing which struck me the most. Actually, it's kind of brilliant white.
Yeah, I've seen. I've been there maybe 4 years ago, and it looks like it's some sort of Mediterranean or tropical, like, hidden island. But
yeah. It's ridiculously nice. It's well worth the trip. Day trip, that is, for the £25 return. Well worth it. Anyway, let's move on to the science. We've got some awesome stuff scheduled for you today. First up, we're going to be talking to Matthew Raybould. Now, Matt is a researcher at Oxford, and he's interested in, the design of drugs, essentially. He's a chemist and a statistician. Really interesting interview, so we'll be hearing from him. We'll also be talking to our favourite professors based on campus here in Penryn, Professor Sasha Dall and Prof Dave Hosken. They're going to be talking like human evolution, which is going to be pretty cool, I think.
Yeah, I think so. They're going to be going through whether humans are actually still evolving.
Yeah, exactly.
Of their debate today.
It's going to be good. Will the Kardashians dominate? That's the question. We'll find that out soon. Also, we do touch a little bit on our chances in love. Do we all have a chance in love, Sam? What do you think?
You got to hope, don't you? You have to hope.
Exactly. So that's coming up. Also, on the music front, now this is exciting. Sam, you're going to love this. We've got brilliant chap, Lewis Island. He records as Aerial Vex. He's a solo rock musician, okay? Brilliant guitarist. We're going to call him up, chat to him a little bit, get some of his tunes on. And see how that goes. We've got lots of tunes for you today as well.
And as ever, we have traffic and weather. From myself with Ben's wonderful jingle.
Absolutely.
And actually we have a question sent in by my younger brother, so stay tuned to that as well.
Excellent. Yeah, we'll be covering that. Nice one. Okay, cool stuff. Well, let's start then with the first part of this interview from Matthew. This is in 2 parts, so don't go anywhere. It's great stuff. Let's put that on for you now.
My name's Matt. I'm currently working in the Department of Statistics at the University of Oxford. My major interests are basically anything to do with pharmaceuticals and developing treatments. So the work we're currently doing in our lab, but when I say lab, it's mostly on the computer, but it's mostly in modelling what are known as biologic drugs, and I'll explain that when we get in the conversation a little bit later. Sure. Essentially, we're looking at a novel class of therapies which, for a long time, we didn't think we could make. Essentially, we're mimicking the body's immune system here, and it's incredibly complex. These molecules are very intricate, but we've now, in the last 10 to 15 years, got it into industrial companies, the ability to manufacture these on a large scale. So we're doing statistical analysis on these systems to try and help them create a pipeline to deliver new drugs to market. So my background is chemistry. I'm now mostly doing statistics and coding and mathematics, so that should be a lesson that just because you pick something for undergrad doesn't mean you go on to do it for the rest of your life.
What fun.
They really are encouraging people to transcend boundaries now. The idea that you stick in one field is very much a thing of the past. So yeah, get prepared to do some coding and to do some mathematics at any point you can. It will help you going forward.
Let's contrast this with kind of what we kind of used to think about if we were to say, the discovery of drugs. For example, let's take penicillin. I mean, this clearly wasn't a drug that was designed in the first place, was it? It was discovered, almost, well, by accident, as the classic story goes, by Alexander Fleming, of course. But it was just discovered to have this particular action, and of course we started using that before we really understood exactly what it was doing. And this kind of sounds to me like it's the other way around. So you kind of start by assembling a particular molecule to deliver a particular function, if you like, in the body.
That's completely right. Yeah. So the technical term for this is that we're moving away from a kind of fortuitous happening upon treatments, and we're now going towards something that's known as rational drug design. So we're trying to use predictable measures that companies can say, okay, we know this pipeline works, we know this will give us good drugs, and we can explain why these medicines are working, and that's really crucial for investors to put the money where their mouth is. And so things like penicillin really were fortuitous discoveries. And again, that was in the class of drugs which we know as small molecules. So small molecules are really what most chemists do. You drive past a chemistry laboratory or a pharmaceutical company, still most of them are working on small molecule drugs. And essentially what this is doing, these are much smaller compounds that we know will have quite predictable properties. They'll be soluble, and they'll probably be able to be taken just as a tablet. And essentially what they do is they mimic your body's antibodies, as they're called. These are the biologics that your immune system produces to combat foreign entities. But they're very complicated. So this system has been developed over many thousands of years of evolution by your body to combat foreign entities. If we can actually start designing these, then surely it's going to be a good therapeutic. There are issues, which we'll come on to, I'm sure. But small molecules are all about trying to happen upon, by rational design, smaller drugs that will do the same thing as your body would do naturally. Whereas now we're kind of moving towards trying to design molecules which could theoretically be produced by your body to combat disease.
I've got an example of it actually. Let's see what you make of this one. You can tell me if I'm correct or not. So okay. the drug Eylea. So I used to work. I did an internship for a medical writing company a while ago, and one of the drugs that we worked on actually at this company, just doing promotional materials and things, was Eylea. Eylea is actually used for macular degeneration, and essentially, I think this to me sounds very much like a good example of what we're talking about here. This kind of this drug design. Essentially, what it does is what they did was merged. They took pieces of an antibody, basically, and to that attached domains of molecules specifically designed to essentially fit and stick to a particular protein in the body, and that was a good thing because of course that inhibits that particular protein from working, and that's the kind of general way that things are working, aren't they? When we say we have a drug for something, usually what that means is that you've got something which somewhere in the body will attach to a particular protein and deactivate it, whether that protein be in the body already and it's natural, but it's still producing an issue for whatever reason, or whether that be in a bacterium or in a pathogen or whatever.
As you say, we have drugs and we have drugs, right? So we have drugs that we take, like paracetamol, ibuprofen, painkillers. These don't treat anything. They don't target a specific molecule. They don't try and stick to a molecule and stop it working if it's gone rogue. Sure. What they're designed for is just to make you be able to bear the symptoms whilst your body gets its act together and your immune system works out a way of designing an antibody which will stick to the molecule that's causing an issue, and be that a virus particle or whatever, it will clear it out of the body and you'll recover, which is why you have this lag time between feeling ill and actually recovering, because that's your body trying all these different combinations of antibodies that it can produce to find one that will finally stick like Velcro to the virus or that's causing the issue, and then you'll start to get better because your body knows how to tackle it. And oftentimes, if you come into contact with the same virus again, your body can actually remember what tactic it used to defeat the virus, and that's why if you get the illness again, you recover a lot more quickly because your body has some sort of memory system, which is incredible and incredibly complex. So your ILEA treatment is using the specificity of an antibody. So this is the fact that your antibodies will bind to a specific target. Now, this is really important when you think about side effects in the body. So a lot of the small molecule drugs that we currently design hit a lot of targets within your body, hit a lot of proteins. So they might hit the one you're after and stop you being ill in that sense, but they may also create unwanted effects in other organs of the body. So you'll often read those scary packets inside your tablets that say, don't take if you have this, that, the other. That's because they can sometimes affect, and if you get any symptoms, you should report them. That's because these drugs are not specific on the whole. We are mimicking very complex molecules with very simple molecules. And so there will always be a certain probability that we'll touch something we don't want to hit. So, which is one of the big attractions of going towards antibody therapies such as ILEA. ILEA is actually a very interesting therapy because not only is it an antibody therapy, but as you said, they cut off the bits of the antibody that make it specific, and also tacked on other little bits to it which attract other parts of the immune system towards it. So not only did it stick to the molecule, but it also acted like a recruiting agent, a very efficient recruiting agent, like a sergeant in an army barking at its troops to get in order and to clear out the drugs. So you can do all sorts of things with these antibody therapies, which is why they're definitely worth studying and definitely worth learning a lot more about.
It sounds extremely complicated. I guess to deal with that level of complexity, you've just got to turn to basically computational methods. Could you maybe explain a little bit about what that really entails? You said you basically do mathematical modelling for these systems, do you?
Well, if you think about trying to rationalise a treatment, then you really need to first understand what's going on, but then to do it on the scales that they need to do it in industry, it's really advisable to turn to technologies such as computers that are designed to churn through algorithms and assess loads of potential drugs and give you quite clear answers as to which ones you should consider developing and which ones are likely to be dead ends. Now, computation may be in its infancy pretended to be the answer to everything, and we won't have labs in the future because we'll know everything and we can predict it on a computer. The reality of this has been a little bit more, people are a lot more realistic these days. We can see the role for computation in the research, but it certainly isn't something that's going to replace experimental work. It sits alongside experimental work in statistical studies, like what our group does, where we can add it as another step on the pipeline. They come forward with a library of their compounds, and we can do certain analyses on which certain properties of these molecules that are typically good in drugs and ones that are typically bad. And that helps them make a more informed decision about which they go on to actually study. Because it's expensive to take a drug from the stage of saying, oh, this might work, to testing it out in the lab, to then actually putting it in patients as well, which are known as phase 2 and phase 3 clinical trials. And then ultimately to getting it approved. These are very expensive processes. So every time you bring a drug that you don't really know how it's working through this step, there's a lot of uncertainty there. You may be wasting millions and millions of pounds. So the computational methods are varied. Some try and model the actual structures with physics and work out how, we talked about molecules sticking to proteins, all the little interactions that are causing that sticking effect, all the little repulsions, all the little attractions, and they try and model the minutiae of the interactions. So you can take it to a company and say, I think this drug will stick to this protein, and I think it will do it in this way, in this orientation, that sort of thing. And that makes up the bulk of computational methods in drug discovery.
I guess the key thing here is actually just simply prioritizing molecules which you've got available for testing. Because as you've said, I mean, obviously all of this
is it takes an incredible amount of funding to actually get the drugs all the way through the initial kind of time point where you think, oh, okay, this might be a good drug. But we're talking years, aren't we? We're talking years. We're also talking, well, lots of funding, essentially.
Well, funding and man hours for sure, because the idea is to get these things out on the market and into patients as quickly as possible. Some of these diseases that they're using antibodies to treat are illnesses for which there are no other therapies.
Sure.
Things like multiple sclerosis, things like rheumatoid arthritis, diseases for which we have no cures. We only have drugs that perhaps slow down the degeneration of the disease. And there is it's really time critical getting this stuff out. So it's a serious side to it too.
Matt Raybould, ladies and gents, don't go anywhere. He's going to come back in a minute and explain a little bit more about the kind of future possible challenges facing this field and the kind of things to keep in mind as well. Interesting stuff, really interesting stuff. It's amazing to think this is all going on in the background, to bring all of these drugs out into production. I didn't really consider before just how complicated the process that is, and just how time-consuming and expensive it is. And we can thank chemists like Matthew, right at the forefront of their fields, to go ahead and do that research that's actually necessary to get these drugs into circulation ultimately. Before we carry on, before we hear from him again, just got a little medicine-related song for you, actually.
I'm looking forward to this.
You're going to like this, Sam. This is by an artist, Stephanie Mills, from the 1980s.
Never heard of her.
No, well, it's brilliant. Matthew, if you're listening, this is your theme tune, mate. We've decided. Give it a listen. Funky stuff, Sam. Yeah.
Stay wise to you. Shady walks and midnight stops have showed me what to do. Kept my cool, this ain't no fool. You think you're messing with? I know how to keep you out, cause I know where you've been. You think that they really want just you. Better think again, better think again. I'm the only one knows what to do. You've been bad, baby, oh so bad, baby, and there's only one thing can be done. You need a little bit of this medicine, just a little touch, yeah. Mama's gonna give you some medicine. Ooh. You need a little bit of this medicine, just a little touch, yeah. Mama's gonna give you some medicine. Every time I think you're mine, you're up to something new. I've done almost everything to try to get to you. All my friends are just dead ends and are helping me along. I just keep on wondering, what am I doing wrong? There is only one thing left to try. Do it again. On this figure, I'm sure I can rely. Mama's gonna give you some medicine, just a little touch it. You need a little bit of this medicine. Mama's gonna give you some medicine. Mama's gonna give you some medicine. 'Cause you've been bad, baby, oh, you've been so bad. There's only one thing can be done. Take your medicine. Doctor's here. Take your medicine. The nurse is here. Don't you wanna get cured? Take your medicine. Take your medicine, baby. Take your medicine. Take your medicine, honey. Take your medicine. Oh, come on. Take your medicine. Go on and take it. Take your medicine. Go on and take it. You gotta take it if you want shit medicine. You gotta take it. If you want shit medicine, you gotta take it. If you want shit medicine, You gotta take it. You need a little bit of this medicine. Mama's gonna give you some medicine. Mama's gonna give you some medicine. Hey, I got all the medicine. You need a little bit of this medicine. Mama's gonna give you a touch. Mama's gonna give you some medicine. Come on, baby, take your medicine. You need a little bit of this medicine. I got the cure. Mama's gonna give you some medicine. I got the cure. You need a little bit of this medicine. Mama's gonna give you some medicine. I got the cure. You need a little bit of this medicine. Take your medicine. Mama's gonna give you some medicine. I got the cure, you know I do.
Now, come on, that is a
Funky,
brilliant tune, isn't it?
funky.
Oh, it's good. Right. Anyway, let's carry on with the science theme then. So we're talking to Matthew Raybould about drug design and kind of the forefront of the field, really. Now he's going to continue to talk a little bit more about this to us. This time, kind of with future challenges or current challenges and possible future directions that this research might take. So let's listen to him again now. This is Matthew Raybould from the University of Oxford.
You'll see a lot more of these antibody therapies emerging into the market. As I say, particularly for illnesses where at present we have zero other alternatives. Antibodies have their weaknesses when they're actually in the body in concentrations, in sort of drug-like concentrations, not lab testing-like concentrations. They can actually stick to one another, and predicting this sort of, I think it's called aggregation, predicting these aggregation properties is something that we're not particularly good at the moment. So a lot of these antibody therapies are getting to the third phase of clinical trials, and they're actually not working. Not because they wouldn't work if they got to where they get to, but because they're not getting there because they're sticking to themselves and they're getting cleared out of the body. Another issue that has been overcome a little bit, but is still a problem, is the problem of the antibodies historically were manufactured by, say you have a mouse and you expose a mouse to a virus, then the mouse's immune system will kick into gear against that virus and produce mouse antibodies. And you keep inoculating this mouse over the course of, say, 6 weeks with this virus. And it keeps producing more and more antibodies, which become more and more specific for the virus. In other words, they become better and better therapies. And then at about the 6-week period, we would experimentally withdraw all those antibodies from the mouse, see the one with the highest concentration, and say, okay, that's our potent, or at least a good starting point for a therapy. But mouse antibodies, if you would put them in a human, would be themselves recognized by your immune system as foreign entities. Your immune system would try and kill the therapy because it recognizes that it isn't a human thing. So this is a problem of clearance, and has led to a technique called chimerization, where essentially we take the bits of the mouse antibody that are doing the cool work and chop them off and stick them onto a human scaffold. Antibodies are Y-shaped, with the arms being the locks in the lock and key mechanism, or the things that stick to these proteins. So we use mouse arms on a human stalk, if you will. And that gives us more time, that gives the body more of a challenge to spot that this therapy actually is actually foreign.
Yeah.
So these are kind of hybrid techniques that because we're using them now, we're getting a lot further towards an antibody therapy than we were in the past. A problem that's still ubiquitous with antibody therapies is that they have to be intravenously delivered. So you can't take an antibody tablet because it gets broken down in the stomach. There are methods to try and do that with because our methods of delivery are getting better. Tablets, you can purposely create tablets which take a very long time to get broken down, even in the acidic conditions in the stomach, so that they eventually do get to where they're meant to go to. But ideally, you want to deliver these intravenously to the target, which makes them less of a thing you can do at home and more of a thing that you could imagine that you have to go to hospital for. So all of these are challenges to be resolved in the future. Computation works at the selectivity stage at making sure that we can sort of rationally design these antibodies. And increasingly, statistical searches are useful for properties such as aggregation, because we can say, even if we can't fully predict the interactions that would cause something to aggregate, we can say that this molecule is very similar to these other molecules which haven't aggregated, or it's very similar to these molecules which are known to have aggregated. And this sort of information is crucial for industry partners, so they can take that data from this huge database of compounds and say, we're pretty confident that this won't aggregate, rather than just going into the process blindfolded and finding out in their phase 3 trial that the study didn't work. And having spent millions of pounds down the line, they then go bust. That helps nobody. So these are the sort of challenges for the future. And experimental groups and computational groups alike will have a huge role to play in bringing this new therapeutic to market.
Brilliant stuff. Well, it's all obviously extremely complicated, and thanks very much for giving us a bit of an insight into this world. I'm sure listeners will be looking out for this kind of thing now, knowing that it's all going on in the kind of background, all the stuff behind actually getting these new drugs out onto the market. I'm going to finish, Matthew, if that's all right with you, with the coolest thing that I think is loosely relevant to what we've been talking about. So of course,
it's not a chili test, is it?
No, not a. Well, you could pop into the studio, mate, or maybe we could mail you some chilies. They were quite painful, I can tell you that. Those hot ones. No, not a chili test. No, you've heard about the. So we've been talking obviously a lot about the adaptive immune system, as we've been talking today, because of course the adaptive immune system is what comes into play to essentially produce these antibodies which gain specificity to particular target sites, whether they be on pathogens invading the body or whatever. But I think one of the coolest things to me in a recent discovery in microbiology, moving away from humans now, was that adaptive immune systems were actually discovered in bacteria, the CRISPR-Cas system, which I think is absolutely incredible. Essentially what it's doing, and this is the remarkable thing to me, because of course the adaptive immune system that we're used to, that we have in us, it doesn't make any genetic changes. So these are just protein-based changes. So in your own lifetime, you come across pathogens and you basically make these proteins, these antibodies, and you basically save them, don't you? You store them almost.
You store the recipe,
for future use. But what the CRISPR-Cas system does in bacteria, it actually saves information into their own genomes, which I think is quite incredible. So what I mean by this is if a virus invades a bacteria that has a CRISPR-Cas system, the bacteria actually removes segments of the viral genome and inserts them into its own genome, and then uses that stolen sequence, if you like, termed a spacer, when it gets integrated. It uses that stolen sequence almost as an antibody, so as a kind of marker to direct machinery back to those viral strands, which I think is incredible.
And you're right, all this in the human, it doesn't happen at the level of the genetics. They're just stored almost like little reminders, almost post-it notes within the body, rather than actually changing the fundamental coding of your immune system. That's really incredible. I had as I say, being a chemist and moving into the field of biology and then moving into the field of statistics, I'm new to a lot of this stuff, and I've heard of CRISPR-Cas, and a lot of the all things get hyped up when they're first discovered.
Yeah,
and gene editing is obviously, you can imagine, quite a controversial topic in science right now, because again, editing your genome to do things like this may theoretically work fantastically well, but there is the ethical question as to whether we should be playing God, so to speak, and actually changing genetic codes, which happens clearly at the bacterial level. Yeah. Of course, what we have to consider is all humans evolved from bacteria, so the system we have now is arguably arguably better for what we need it for than the bacterial system. Through evolution, the powers that be have determined that we are no longer using our body has no longer got this capability. It uses a different mechanism, and that may well be because of a reason that we don't fully understand yet. We are far, far more complex than the single-cell bacterial organisms. So there's still so much to understand about the immune system out there, and immunology is definitely something your listeners should get into, and if they're young, then go on and study at university, because it's such a hot topic right now, and it's got an academic excitement to it because it's really cool, and it's also got a huge industrial aspect to it as well, because everybody wants these new therapies to come out to save people's loved ones and to help people live with horrible diseases.
Exactly.
So it's great for the mind and great for the soul.
Yeah. Well, I mean, it's no silly thing to say. I mean, when when we traditionally think of becoming a scientist to save the world kind of thing, well, if you do something like what you're doing, you actually are doing that. You are working ultimately to help people, to save people from various diseases and things. So
that's it. You're a small cog in a big machine, but you're working towards something that's definitely worthwhile.
Absolutely. Well, Matthew, thank you very much for talking to us today. We'll have to get you back on. We'll have to get you back on again soon. You realise that you're not escaping from a regular appearance.
Well, this is the second time on the second Cornish radio station.
Exactly. So, well, you've heard it.
I must say though, I've never ventured quite as far as Cornwall. I've only ever gone as far as Devon. I am a Midlander myself, so it's a good 3.5 hours to get to Devon, and I gather it's about the same again to get to Cornwall. But with the view you just showed me outside your recording studio window, I could definitely be persuaded to pop in.
Oh, it's well worth
beautiful part of the world.
Well worth the extra couple of hours from Devon, I assure you.
I'm sure your listeners will agree.
Absolutely. Well, Matthew, thanks again, mate. We'll chat to you again soon.
Wonderful, thank you, Ben.
Thanks very much, Matthew. That was Matthew Raybould from the University of Oxford. Sorry. Now he's going to be joining us again in a few weeks, so do stay tuned. Now, there's not really much time to explain much else, is there, Sam? Because we have just received an urgent report.
Some travel updates, because we've got some urgent travel.
Right, well, I better get on your backing as soon as possible, because this really is important.
The weather.
If only we could speed it up, mate. Because
no, we're not speeding this up.
With Sam. Steamy.
Oh, there's no time for this.
There's always time for this.
Just in the studio. Weather and travel. Take it away.
So today we're going to start with travel because of the urgent travel update, and it's on the Treview Road in Camborne. There are reports of a shed load of milk bottles. Please approach with caution.
Could you just repeat that?
That is a shed load of milk bottles. Approach with caution. On the A390 Higher Towns, which is Truro, there's heavier traffic than normal, and all along the A390 there's heavier traffic than normal. Travel time is 20 minutes by 3 Milestone. On the A39 in Penryn there is queuing traffic currently, and the A30 by Blackwater, the traffic is finally smooth. So if you were worried about the traffic earlier, it's got better. Moving on to weather. My chair's just given way. Moving on to weather. Today it will be cold and frosty, but there will be plenty of sunshine, so it will be a nice day. Just maybe take some gloves. Thank you very much, Ben. But remember, a shed load of milk bottles. Approach with caution.
Yeah, okay. Well, thank you very much, Sam. Brilliant stuff. Let's catch the end of that jingle. Okay. Right, well, thanks, Sam. Okay, before we move on, so I promised you earlier that we're going to hear from the profs in a minute, the big boys, talking about human evolution and whether humans are still evolving. Very interesting section. But first, I think I'd like to give this a try. Sam, what do you say to this? Okay, I've got a great idea.
Yeah, let me know.
So I like to call this section a new section. Okay, I'm just putting this out there. Listeners, tell us if you think this is a good idea. This is called the haunted telephone. Okay.
All right.
Now, what we're going to do is we're going to call someone at random, of course. No warning, of course. The problem is, though, I've heard reports that the phone is actually haunted, mate.
What, the studio phone?
Yeah, the studio phone is haunted. When you try and give someone a ring, it's really weird. I get chills running down my spine, and for some reason, this music seems to start playing. Should we give that a listen now?
Let me know what the music is.
Yeah, it's this.
Just on its own, this just starts playing.
It's spooky.
It's terrifying.
If you listen really carefully as well, you can sometimes hear. Anyway, I don't know what to make. I don't know what to make of that.
To make it up.
Do you? Well, I'll tell you what, Sam. I'll leave you to smooth talk the listeners a little bit.
All right. So
what I'll do is I'll give. Should we give Jared a ring today?
So yeah, we'll get Ben calling up Jared
All right.
at the moment. So I think he's just heading over to get the phone out.
Take us away. I mean, you could give us I don't know. We've got science questions, science facts, anything like that.
Yeah. So actually, today I received a text from my younger brother, who's Matthew, up in London, and he's asked a question. You might have seen recently that the White Zoo in Austria has announced the birth of 4 white tiger cubs, and he's actually asked why are these tiger cubs white, and so. As we know, there's 9, or you might not know, but there's 9 subspecies of tiger, and these white tiger cubs that were born are Bengal tigers. So they're the most, the widest spread and most numerous species of tiger, I think. And as you probably know, tigers are normally orange and black, orange with black stripes, and this coloration has evolved to allow tigers to camouflage in their foresty environments or grassland environments where they live in South Asia. However, white tigers, which are naturally occurring, are much worse at blending in with their environment. So normally you'd expect that these white tigers would then be lost from the population because they'd be naturally selected against. However, they still seem to persist. So what is it about white tigers that means they remain and means we have them in zoos today? And the reason that they still exist is because the whiteness is caused by a single gene. So interestingly, it's a gene that's only present in one single location, and the change is caused by one change in a letter sequence. And that change gene only works, it only causes this whiteness if it's received from both its mother and its father. So when you receive every gene in your genome, or in a tiger's genome, is received from both its mother and its father, so you get 2 copies. And because this gene is recessive, it means that you need to have both copies of the gene for the tiger to be white. This means that tigers can go around carrying this gene, which would normally be bad for them. So this being white is bad, but you can carry the gene without it actually causing the tiger to go white, which means it's allowed to persist in the population. And when you breed 2 tigers that contain this gene, if a mother with the gene and the father with the gene, if the offspring contains both copies of the gene, then the tiger will end up being white. And so most of the tigers that you see in zoos nowadays that are white, they maintain these white tigers by just inbreeding 2 white tigers together. Because if you breed 2 white tigers, you're guaranteed to get white baby tiger offspring. Ben, how's the phoning going?
Well, no luck so far. He's not answering. Let's give that another shot. Shall we?
Give it one more try, and if we struggle, then I'll play a song for Matthew, who sent in that question. Anyone else who wants to send in a question, go ahead.
It's okay. Stay on the line. This is going to be well worth it.
Stay.
Come on.
Let's see. He's not answering.
He's going to answer. I know it.
So I'll line up a song just in case.
Good plan. Give it a mo.
All right, here we go. He's calling.
Oh, hello. Let's connect it
right,
through in case.
We're going through. He's connecting it. Let's hear the ring.
Okay, let's get the haunted phone.
Will we get an answer?
Jared.
Can't take your call at the moment.
I tell you what, the haunted phone could leave a message.
We'll leave a haunted message.
At any time.
Well, unfortunately, we couldn't get through to Jared there, but never mind. Maybe next time. Shall we play a song? Just this one's for Matthew for calling in. He's a big fan.
You got a song? Excellent. Let's give that a shot.
I'm so into you, I can barely breathe. And all I wanna do is to fall in deep. But close ain't close enough till we cross the line. So name
Nice stuff. Good choice. Very good choice.
Thanks for the question, Matthew.
Yeah, good choice, Matthew. I like your taste in music, mate. It's brilliant. Sam, I don't know how to break this to you, mate.
Yep.
I've just received a message.
Who's it from?
Well, this is from our number one fan, Dan. Shout out to Dan.
Thanks for listening, Dan.
You're not going to be happy, though. I'm really sorry, Sam, but he says, about your weather report, he says, frosty. Is Sam looking out the window?
Well, thanks for the message, first of all, Dan. It's nice for you to listen, but we're all doing our best. And I'm just giving you the facts that I know. It's cold outside, right? Maybe you're looking out the window from your cosy house, but it's cold outside, so maybe step outside, Dan.
Just no respect for weathermen.
No respect.
No respect for
We're all doing
weathermen.
our best. We don't get it right every time, but we try.
Right, let's continue with the science theme then. So right at the beginning, I promised you that we'd hear from the profs talking about human evolution. Yes, that's right. The time has finally come to hear that interview. It's great stuff. Give this a listen and let us know what you think.
So for evolution to occur, you need genetic variation, you need genes for stuff, and then you need selection to act on that stuff. So if you've got those two attributes, you've got selection on something, and you've got genes for that same something, then evolution will occur. What selection is differential reproduction, so different numbers of children. So if you've got different genetic variants that have different numbers of children, then you'll have Darwinian evolution. So I don't think there's any reason to suppose that humans are different to anything else in that everywhere we look, we find genetic variation for stuff. And we know that humans have different numbers of offspring. And so we would expect then that there is evolution occurring, adaptive evolution occurring. But it's not always clear what that would be for.
Sure. Also, I mean, I think the other point to make is that we're extremely Western-centric when we make these statements. We're talking about the world where the majority of kind of pundits who can sit and write about, have time and space to write about such things, live. And most of the population do not live in a Western world with Western medicine and all of the things. I mean, because this comes from the place that basically, because almost anybody with just a minimal amount of life, if you like, with any attributes, can live to a ripe old age, can have kids. So from that perspective, it kind of intuitively feels like the whole kind of nature red in tooth and claw and all this kind of stuff, and the struggle for existence, the struggle to leave different numbers of offspring is kind of been left behind us. But you know, there are not that many people. I mean, proportionately, there's 7 billion, 8 billion people on this planet, and less than half of those people live in worlds where this kind of cartoon even applies. Now, we can discuss whether even in the Western world, with all of its benefits, there is likely to be systematic change in heritable variants, across generations as a result of differential reproduction, as Dave has kind of outlined. We can discuss that as well, but I think the other thing to bear in mind is that there's an awful lot of people who are still living with infectious diseases, starvation, problems giving birth, child mortality, maternal mortality during birth, and in that kind of world, there is likely to be a lot of selection still acting. I would say fairly strong.
But there's selection happening everywhere, but Sasha's right in the sense that a lot of this debate comes from the idea that we're no longer part of a food chain, and just because we're no longer part of a food chain, using kind of stupid shorthand. People assume that there's no selection, but that's absolutely 100% not true, because different people have different numbers of children. If those same groups of people keep having different numbers of children, then we're seeing evolution for whatever those traits that underpin that differential reproduction are. So a paper that came out recently on, I think it's Icelandic data, they used whole genome sequencing. This is where they look at every gene in your body and they look at variation within the whole human genome. They find genes that are associated with things like educational attainment, things like wealth, things like how well you do at school. Now, that doesn't mean we've got genes for how well you do at school. It means that there are some genetic attributes that feed into how well you do at school. And the interesting thing about that study is not that. What they find is that there's selection against those things. And in a sense, we know that poorer people tend to have more children than richer people. If being rich or poor has any biological basis, however small, then there will be selection against the traits that make you richer and selection for the things that make you poorer, because poor people have more children.
And just to clarify, I mean, when you've got a Western world where the kind of relative, because we probably have the demographic transition, which is kind of lies at the heart of what Dave's talking about, which is where as societies get richer generally, or as any individuals get richer, they tend to have fewer children, and it's probably got good kind of a good adaptive Darwinian basis, in the sense that through most of our ancestral history, the more well off you are, the more you should start concentrating on a few offspring to get them in really good state so that they can dominate the societies that they live in and all the rest of it. They can leave better offspring that are going to survive more.
It's a quality-quantity trade-off.
In the Western world, though, given this cartoon that we talked about now, where basically you don't really have being good quality doesn't necessarily, like being very rich, won't necessarily lead systematically to leaving more progeny that are themselves going to reproduce at relatively high rates. Then you have this. Then basically, what previously was an adaptive trait could become a maladaptive trait, which may be what we're seeing here. Yeah. Now, I'm kind of skeptical about some of these studies. I'd like to see kind of more systematic stuff, because there are other things that need to come into play here. I mean, one of the other arguments against natural selection acting on humans is that we're predominantly cultural species, and that, I mean, this is the big argument against thinking of humans at all from a biological perspective, because the sense is that almost everything that we are and we do is determined by our culture, by the kinds of attitudes that we grow up with and we see around us. Now, that is patently too simplistic and cannot be true for a range of reasons. Gene culture coevolution is actually a very, very potent force in humans and leads to what biologists typically would call evolution, which is change in gene frequencies. Now, you can argue that there are other types of evolution and that we should be a bit more inclusive, especially with humans, to include things like cultural variants and things. But if you're just going to stick strictly to a biological definition of evolution, which is just the change in frequencies of genes across generations, or the change in frequencies of inherited traits, if you like, then culture will play a role, and we know there is well documented for a couple of things, and very physiological stuff, not just behavioral stuff. So, for example, milk digestion is now widely accepted that the ability for humans to continue to digest milk beyond weaning, which is very weird for mammals, because milk is not a widely available resource for most mammals. It's very specifically produced by mothers to provision their offspring with, for very good reasons, and there are lots of kind of detailed reasons why they would do this, and when it's a good thing to do and when it's not a good thing to do. But it's a very costly thing for mothers to do, so they won't overproduce it. So there's almost never a net kind of production of milk in a population for it to be a resource to exploit. But what's happened is, it seems like there have been 3 independent origins of mutations that have allowed humans to express the lactase, this kind of particular enzyme that allows you to digest the sugar in milk, to continue to be expressed beyond weaning, and at variable lengths. So actually, you may know people who suddenly develop lactose intolerance, and in fact, the older you get, the likelihood is that you'll probably there's not an insignificant chance for anybody from any population to develop lactose intolerance, because of basically what the selection was on this persisting, but within the time frame that matters from an evolutionary perspective, which is
sort of to summarise all of that, is there's been selection for us to keep a gene turned on that used to only be turned on in kids, and that's happened 3 times in our evolutionary history.
And it's been very strongly linked to the cultural practice. It's very clear that this is socially learnt and socially transmitted.
Milk, cows,
so
sheep.
it's keeping of domesticated herbivorous mammals, basically. And there's one in Western Africa, there's one in India, and then there's one in kind of southern Europe. And these loci, these are kind of foci now where people who belong to those lineages, people who show very high levels of lactose tolerance through our lifetime, but then other parts of the world where the population is made up with people who don't come from those lineages, that's where you see the kind of high levels of lactose intolerance. So to expect everything to be static, and this notion that there's a kind of platonic norm human that's going to now persist in perpetuity, well, that kind of cartoon of the world should have been killed by Darwin, even though it still persists, intuitively. But everything is actually pretty dynamic. Who you are as a lineage is going to be changing continuously. Now, whether or not it's changing in a systematic way that you can relate to specific kind of problems to be solved or that have been faced by that niche is, the degree to which that happens is the thing that's interesting and occupying most evolutionary biologists now, I would say.
Yeah. So I think as well, maybe we're kind of stumbling across a kind of bigger general problem here, that it's a general kind of unwillingness for people to apply kind of well-known biological ideas and biological ways of thinking to humans.
Medically, there's also this issue that we, there's a lot of evolutionary change going on. Maybe not, in humans to a certain degree, but also in a lot of things that affect us. And so Darwinian medicine is coming to the fore because of
agriculture, everything.
Yeah, because of the problems with the antibiotic resistance, which is an evolutionary problem. Basically, the way that we've been dosing ourselves up with medicines has selected very strongly for things to sort of cope with those medicines and thrive even when we pump ourselves full of antibiotics. And people are realizing that we really need to really truly embrace the kind of details of evolution to be able to even maintain the kind of lifestyle that we've been enjoying.
And the problem is that the details are where it gets tricky. But even the simplest axiom of evolutionary biology, which is so simple that you could explain it to a 4-year-old child and they would understand, people struggle with that. And that's basically, you apply selection to genetic variation, you get a response, and that response is evolution. It's very, very simple. But if people refuse to accept, for ideological reasons, through lack of education, through lack of understanding, the most simple of these starting points, then when we get into the more nuanced detail of what we're doing and what evolution's doing to us, that gets much, much harder to even bring to the table, I would say.
Yeah. And then I guess the other kind of big area that's likely to be, just to drag it back to the kind of the focus and be slightly less philosophical about things, another probably likely strong source of selection nowadays is probably sexual selection. Actually, it wouldn't surprise me. And this is another process that, if you reproduce sexually, if you're whereby when you're producing offspring, it involves combining genetic material with at least one other individual. That process, as soon as you have that, you'll pretty almost certainly get some sort of differential success in that endeavor. Yeah. and that can be extremely arbitrary. I mean, it can operate in the absence of any strong what Darwin called natural selection, or if you like viability selection, the kind of selection for solving concrete environmental problems. It's just the nature, the fact that we will always have to find somebody else to reproduce with. That
the peacock's
process,
a case in point, actually.
Sure. That process, the fact that you have to get somebody else to agree to sort of mate with you, there are very likely to be differential success in this, and that's likely to persist. That's likely to be the case now, in 1,000 years' time, in 1,000,000 years' time, if our lineage lasts that long. That's likely to be there.
Think about Mick Jagger's reproductive success compared to mine. You know, Mick's had more children than I have, and it might have something to do with his wealth. Who knows?
Well, I mean, Genghis Khan. I mean, they've done the analysis, right? Genghis Khan is progeny is very highly represented in modern Eurasian populations. I mean, I think up to a third of Eurasian populations, something like that. I can't remember the exact statistic, but it's something quite staggering. Can trace their lineage back to Genghis Khan. So it's that kind of stuff.
That probably explains a lot of fights in Falmouth pubs on a Friday night, actually. But it's slightly sidetracked here.
Exactly. But now, of course, we could be having. I mean, sexual selection could be going in the other. Could be acting in another way, in opposite direction, according to that study that Dave just cited, where the more successful people, culturally successful people, the people that are accumulating most wealth or that are accumulating, that are kind of becoming most attuned with the world and spending a lot of time studying it and understanding it, those are the people that are leaving fewer offspring. So it could be that the reverse is going to be true, and that we're going to go through a cycle where the average Joe on the street, or it's actually likely to be the kind of Kardashian progeny, are likely to dominate, say, future generations more than, say, Einstein's progeny.
Well, in the land of the blind, the one-eyed man is king. So indeed. You never know, Sash. You never know.
Well, it is. I mean, the nice thing about this kind of arbitrariness of sexual selection is that we all have a chance.
Yeah.
Very reassuring.
The punchline is humans are still evolving and will continue to evolve. It might just be that the selective forces that are operating on us now aren't quite the same as those that were operating on us historically, but we are still evolving, no question.
And also, I mean, I think the other thing to take from it too is like all of the kind of fantasies, the utopian fantasies about how we'd get brainier, we'd get kind of more physically adept, and all these kind of ideals.
Well, this is what that study shows, is exactly what's not happening.
Sure. But I mean, I think this boils down to something that is really important to take away from thinking about the world from an evolutionary perspective, is it's not about individual quality in a kind of in any kind of arbitrary cultural sense. It's not about your ability to think carefully or to have a high IQ or anything like that. It's about your ability to leave copies of your heritable variants. Yeah. Okay, it's not just yourself, because you can also be super nice and not have offspring if that then leads to your relatives having
copies.
So you can do it. You can do well if you pull together as a reproductive lineage and very close relatives. You get a chunk of them that just spend all their time getting resources, fighting off other individuals, and leave a couple of individuals to just be super fecund. That can also win in the world, but it is about the differential success of your lineage's ability to get its heritable variant, to get itself copied, to get itself persisting at a higher rate relative to the other. Again, this is another thing. It has to be relative to what's out there at the time. It's not an absolute thing. There isn't an absolutely best thing to do.
Everyone else has one child and I have two, I win.
So, and this is another thing to say about the demographic transitional world, like modern Western societies now with negative growth rates. The more we even the playing field, if you like, in this modern Western way, actually, the opportunities for selection are actually going up in one sense, because you're making the playing field a much easier playing field and things like arbitrary sexual selection stuff can get going really easily in that world, because often with sexual selection it runs into point where, like the peacock's tail, where the tail just gets so long that even though these males are like super sexy and attracting loads of females, they have such a long tail that they never even get a chance to meet many females, even though in principle, if they hung around and could strut around more, but they're getting picked off by predators because they're so easy to catch and things. So usually it runs into this, usually with a lot of viability selection around, with selection on your ability to sort of do things in the world that are kind of practically good in a sense. With a lot of that, sexual selection can get kind of caught up and can get limited quite strongly. But in a world where you've got relatively little of that, then there's really arbitrary kind of directions that selection can go on, and the opportunities for them I think are probably likely to be more.
Extremely strong case here, listeners, for the fact that really biologically speaking, there is nothing special about humans, and we can and do apply Darwin's ideas to the evolution of humans. I think we can probably finish it there.
Absolutely.
Did you agree? Yeah.
Well, we are special in the sense that any species is, by definition, special. We're not so special.
Not unique.
We're not so different that the ideas that have helped us understand the natural world do not apply.
Great stuff. Well, thank you very much to Sasha and Dave for that discussion. Main thing from that for me, that really encourages me, is thanks to sexual selection, we all have a chance in love. What do you reckon, Sam? What do you think?
I think it's really interesting. I think the take-homes of that debate are that I think we can all agree that humans are evolving, like most things, isn't adaptively evolving. But I think the direction of evolution that humans are taking at the moment is, in the Western world, potentially different from in other third world countries or less developed nations.
Sure. Yeah, it was interesting how they brought kind of culture into that. I guess it's kind of obvious that should play a major role, isn't it? Because culture defines everything around us, really. Anyway, moving on. There was a request put through,
and I've these professors, they won't come on our show unless they get to request
unless they get their own individual tunes. This one was from Dave. Actually, he said, don't even think about using that section unless you play this song for me. Dave, if you're listening, don't worry, we have got your song. I can only apologise to the listeners at this point, but thank you again to Dave and Sasha.
Thanks.
Okay. Yeah. Are we about to get it just a little hot and sweaty in this? Ooh, baby. Ladies, let's go. Soldiers, let's go. Let me talk to y'all and just, give you a little situation. Listen. You see the get hot every time I come through. When I step up in the spot, make the place sizzle like a summertime cookout. Proud for the best chick, yes, I'm on a lookout. So banging, shorty like a belly dancer with it. Smell good, pretty skin, so gangster with it. No tricks, only diamonds under my sleeve. Give me the number, but make sure you holler before you leave.
Like me. I know you do. That's why whenever I come around, she's all over you. And I know you want it. It's easy to see. And in the back of your mind, I know you should be on with me. Don't you wish your girlfriend was hot like me? Don't you wish your girlfriend was a freak like me? Don't you? Don't you?
Quick announcement from Sam. He wants to change girlfriend to, what was it?
Either girlfriend or boyfriend.
Yeah, excellent. Thank you, Sam.
Your girlfriend was fun like me. Don't you? Don't you? Fight the feeling. Leave it alone. 'Cause if it ain't love, it just ain't enough to leave a happy home. Let's keep it friendly. You have to play fair. See, I don't care, but I know she ain't gon' want to share. Don't you wish your girlfriend was hot like me? Don't you wish your girlfriend was a freak like me? Don't you? Don't you, baby? Don't you? Alright, sing. Don't you wish your girlfriend was wrong like me? Don't you wish your girlfriend was fun like me? Don't you?
Okay, I see how it's going down.
Don't you?
Shorty want a little menage to pop off or something. Let's go. Well, let me get straight to it. A broad won't watch it when I come through. It's the God Almighty looking all brand new. And shorty wanna jump in my Aston Van Jewish. Looking at me all like she really wanna do it. Try to put it on me till my black and bluish. You wanna play with a player girl and play on. Trip out the Chanel and leave the lingerie on. Watch me and I'ma watch you at the same time. Looking like you won't break my back. You're the very reason why I keep a pack of the Magnum. And with the wagon hit you in the back of the Magnum. For the record, don't think it was something you did. Shorty all on me cause it's hard to resist the kid. I got an idea that's dope for y'all as y'all can get cool. So I can hit the boat for y'all.
She loves you. I understand. I'd probably be just as crazy about you if you were my old man. Maybe next lifetime. Possibly. Until then, old friend, your secret is safe with me. Don't you wish your girlfriend was hot like me? Don't you wish your girlfriend was a freak like me? Like me. Don't you? Don't you, baby? Don't you? Alright, sing. Don't you wish your girlfriend was raw like me? Raw. Don't you wish your girlfriend was fun like me? Big fun. Don't you? Don't you?
Steamy stuff. Good choice,
That was
Dave.
Don't You by the Pussycat Dolls.
Oh, that's good stuff, wasn't it? Sam, I'm sorry, mate. We're going to break your heart with this show. We've got another comment that's just come through about your weather announcement.
What is it with people nowadays?
I don't know, mate. Well, this is from Dan again. He says, apparently, he's in a T-shirt only on the walk to work.
Well, what can I say, Dan? Like, if you think 8 to 10 degrees is T-shirt weather, go ahead and wear a T-shirt. I'm just telling people, watch out, it's cold outside. So, Dan, this is my message to you.
You're as cold as ice. You're willing to sacrifice our love. You never take advice. Someday you'll pay the price.
That was Cold
take
as
that, Dan.
Ice by Foreigner.
All right, now something very exciting for us now. We've got a musician connected to us on the line just now. We've got Lewis Island, a.k.a. Aerial Vex. Lewis, can you hear us, mate?
Hello there, yes I can.
Thank you very much for joining us on the show today, Lewis. How are you doing, mate?
Yeah, I'm very well, thanks. How are you?
Yeah, good, cheers. We've actually got a couple of your tunes to play next, mate. We've got Fight the Burn and Piece Together. But before we get to that, could we just hear a little bit about what the kind of music means to you? Because I've listened to them before, obviously, and they're really awesome tracks, extremely well produced. Sam hasn't heard them yet, so he's going to be hearing them shortly. Chat to us a little bit about your kind of inspiration behind making music and what it kind of means to you.
Well, I mean, the songs that I'd written were when I was at university. I was an undergraduate student. You know, you're kind of in that mindset where, I don't want to conform to society and everything like that. So I wrote music moaning about the state of the world, as most people do.
Yep, good stuff.
Yep, pretty depressing, but no, I mean, I just like picking up the guitar, I like playing riffs, I like recording them straight away. So a lot of the songs probably aren't that great, but
no, they're awesome. They're awesome, mate.
The ones that are alright are well written. So, and it's easy to record as well, which is good. I just got my laptop in my bedroom, and so it's not really a rock and roll lifestyle, unfortunately, but it's still well produced, which is all right.
Yeah, well, that's the thing, actually. That's the thing I was going to talk to you about, because as we'll hear in a second, these songs, you know, extremely well produced, very professional. But this is all just you on a laptop, isn't it? It's just all.
That's correct.
Yeah, you're doing all the instruments and things as well. It must be quite difficult to do that kind of thing. I mean, could you kind of run us through actually what? I mean, I'm not sure. Maybe people are listening who are kind of interested in doing the same thing. You know, starting out as a solo musician when you don't really have a band necessarily supporting you, but you just want to get your music out there and get it recorded. So how do you go about doing that? Could you run us through that?
Yeah, well, all you need really is a laptop with a decent sound card, decent memory. You get something called a direct input box or whatever. You just plug that in to USB, and you can plug in jack leads from your guitar or your drum kit or whatever. And essentially, all you do is run it up through amp simulators, things like that, so things which make it sound like it's in the studio.
Yep.
And you just mix the hell out of it and hope for the best.
Yeah. Sounds good.
9 times out of 10, it actually sounds like it's been recorded somewhere else rather than your bedroom, which is pretty good.
Yeah.
And it saves a lot of money as well.
Absolutely. Yeah, I mean, if you think about booking time in a recording studio, it's extremely expensive, isn't it?
Oh, yeah, very expensive, yeah.
So why rock and roll? Because it's very much kind of hard rock style that you're kind of interested in, isn't it? As we'll hear in your tunes in a second. Has this always been a kind of genre which you're a particular fan of? Or?
Yeah, well, I just love riffs.
Yeah.
You know, just a little catchy motif, you know, there and again. Well, my dad was the main influence, really. He was in a band, and, you know, he listened to all Led Zeppelin, AC/DC, Black Sabbath.
Yeah,
all
awesome.
That kind of riffy old-time rock.
Still gigs around Anita, doesn't he? Is he still going?
Yes, he's still going, yeah. He's
awesome.
Almost mid-50s now, so he's, you know, just an old musician on the road, going to all the local pubs, so, you know, living the dream.
Yeah, absolutely. Well, we heard from another chap, actually, Gareth, a couple of weeks ago now, who's kind of done a similar thing, just kept playing music, and he said that, you know, it's worth doing, even if necessarily it doesn't have to necessarily be the money that's the main factor that brings you into music. It's just an amazing thing to do.
Yeah, exactly, and just remember, like, even if you're doing it in your spare time and you've got a job or whatever like that, at least you've got a back catalogue to fall back onto if the opportunity came to go and join a band or whatever like that, you know. Just go up and record. Don't worry about, will anyone listen to it now? You know, because people will in the end.
Yeah, exactly. You've always got these, as you've said, you've always got this catalogue that you can build up.
Exactly, yeah.
Well, we're going to hear some of your very tasty guitar work in a minute.
Oh,
I've got a quick question first.
Go for it, Sam.
So where does the name Aerial Vex come from?
Wow.
That's a good question.
Well, that's because I'm not very good at band names, and
no, it's a great name.
Probably a mixture of the thesaurus and random name generators. So there's actually no reason behind it. I probably kind of made a reason up on the spot, but I can't really remember that right now, unfortunately.
That's cool.
It's great stuff. Yeah, I mean, as I was as we were saying, very, very tasty guitarist. So, listeners, if you've just tuned in, stay on the line because we're going to be playing some of this stuff in a second. Guitar skills are kind of through the roof, Lewis. When did you start playing? And do you have any kind of advice for any guitarists out there who might be starting to learn guitar?
Wow, so I started about 13 years ago. So when I was about 12.
Yeah, you picked it up.
I picked up the bass originally, and then I thought, I need to do better than this. So I picked up the guitar. And, just played by ear a lot of the time. I went to a few lessons, just to get your theory up to scratch and everything. But I do recommend you play by yourself first and play a bit by ear because you want to kind of get your own sound. You want to kind of,
Sure.
you don't want to kind of conform to playing someone else's way. So
yeah, that's a nice thing. That's the nice thing about guitar, I think, isn't it?
Yeah. Well, even if you sound rubbish to start with, you just get used to it. So
yeah, have fun. Exactly, it's the main thing, isn't it?
Exactly. Yeah.
Cool. Well, we're going to put some of your tunes on shortly. Last question for you, Lewis. Do you have any more questions, Sam?
No, you take the last one.
No, cool. I was just going to ask you, Lewis, favourite bands, and have they gone into kind of influencing your sound?
Oh, blimey. I'd say Led Zeppelin.
Yeah. Okay.
Band.
Nice.
Yeah.
Nice. The classic rock kind of style. Well.
Yeah.
Thanks very much for tuning in to us, Lewis. We're gonna pop on. Gonna pop on a song now. Which do you recommend first for the listeners? We've got Fight the Burn and we've got Piece Together.
We'll Fight the Burn on first, just to wake people up because it's quite difficult for me to wake up to this call. So.
Awesome. Tell us a tiny bit about this song, and then we'll let you go, and then we'll pop it on.
Well, I wrote it quite a long time ago, so I actually can't remember what it's about. So I think you'll kind of have to. You're going to have to work it out yourselves.
Okay, no problem.
Some catchy riffs.
Yeah, well, we're definitely going to hear some riffs. I know that for sure. I've given it a cheeky listen, obviously, before.
Thank you.
Well, Lewis, thank you very much, mate.
No problem.
We'll probably kidnap you again at some point, mate. You realise this is not a solo appearance. We'll capture you again at some point, all right?
Okay, no problem.
Yeah, okay. Thanks, Lewis. See you, mate.
Cheers,
Thanks very much. Cheers. Bye-bye.
Bye, mate. Great stuff. Right. Okay, as promised, let's put on that first track from Lewis Island, a.k.a. Aerial Vex. Find him on Facebook. Just search for Aerial Vex. Check out his tunes. He's got them on SoundCloud as well. I think you can download them for free, actually, on his SoundCloud. So do check that out. But for now, let's just listen to some pretty heavy riffs. This is Fight the Burn. Brilliant stuff.
Great stuff.
Great stuff. That was Aerial Vex, aka Lewis Island. We just had him on the line. Thank you very much for that, Lewis. Thanks for sending that to us. Awesome tune. We'll finish up with a final Aerial Vex song, but for now, let's bring the show to a close, shall we, Sam? A few things to do before we do that. Actually, one last comment for you, Sam.
Oh, here we go.
This is about your weather again, but this time, you ready? It's a nice one.
Oh,
can you believe it? So Dan says, "Sorry, Sam, I am your biggest fan, really. Thursdays apparently brighten his day for 2 reasons. Number 1, Sam, it's your sweet and soothing voice on the radio.
Thanks, Dan. That's nice of you to say.
Number 2, it's after getting a falafel on campus because." No, are you ready for this? It's because, not because of the falafels, not because of the taste, nothing like that, because he sees you in the queue.
Oh, thanks, Dan.
Touching stuff.
By the way, foul falafel are great. They are really, really great falafels, so if you haven't had one, try it. Yeah,
they are good, aren't they? They are very good. Great. Yeah, well, I mean, thanks very much to everyone who's featured on the show this week. Thank you in particular to Matthew Raybould, who we heard from earlier, talking to us about the kind of right at the forefront of drug design. Really interesting to hear from him. So thank you, Matthew. He's headed for great things, actually. We go way back, man. Me and Matthew, man. Way back. Way back, man.
I find that it's way beyond me, that kind of research. It's so impressive that...
It's incredible.
Pre-drug trial work is just the amount of work that goes into it before it even gets to any form of trial is amazing.
Yeah, incredible stuff. Thanks, Matthew. We'll feature you again at some point soon. And thank you also to the profs, of course, Sasha and Dave. Their channel on human evolution. Very interesting stuff.
Great stuff.
And finally, thank you to Lewis Island for tuning in with us just a minute ago to chat to us about his music making. That was his track we just heard then. We'll finish with one of those as we go out. Just before we do that, Sam, actually, I've just remembered. I've got something for you.
Oh, what is this?
I wrote you a bit of a song, mate. Would you like to hear it?
Yeah, go on.
It's quite romantic. And this, I think, whilst I play this, just imagine that Dan is singing this to you, okay? This is him singing about him listening to your announcements, all right?
Let's hear this.
Okay. Give this a listen, mate.
Sitting by the sea, on the sun fills the sky, wishing you were here, but I know now it won't be long. Far across the ocean, I know you can hear. Outside your window, we'll see the same storm. Kiss me forever, kiss me forever, kiss me forever. Kiss me forever, kiss me forever, kiss me forever.
to be caged and removed. A success in writing, yet nothing to prove. Ashes of hope show my view. I was too blind.